Hello everyone, this is Rainbow John from Geniusescreed, and in this lecture we're going to be simulating a preheat train for the crude oil we modeled in the previous lecture. The learning objective is to simulate a preheat train crude oil. To simulate a preheat train, a crude oil passes through before being fed into the distillation units. And here's the problem statement. But before we proceed to the problem statement, let's correct something from our last. I made a mistake in the last lecture, so let's correct it in this lecture. So we can go ahead and delete this. I clicked on this, then I pressed delete on my keyboard, so I deleted it. Now going back to my properties, then I can delete this blend too. Coming back to my assay 1, this distillation properties was where we had the distillation data was where we made a mistake. This is supposed to be after 60, it should be 70. Edit, after 60 should be 70, then 76, then 80. So 70 should be 450, 76 should be 490, then 80 should be 516. Calculated, then output blend. Let's add and we can install the oil. Let's say this is crude oil. Install, so that should be all. Let's check the tables. Yes, so molar composition, oil distribution. So we are good to go. We can come back to our simulation environment. Then we have our crude oil here. Okay, so let's go back to our slide. Now here's the problem statement. You can just write down the key data that will be needed. A crude stream at 15 degrees Celsius, 1000 kilopascals, and a flow rate of 6 exponential 5 kilogram per hour is mixed with a stream of water at 15 degrees Celsius, 1000 kilopascal, and this flow rate using a mixer. The outlet of the mixer is then heated to 65 degrees Celsius through a heater with delta P of this. The heater outlet is fed into the tube side of a shell and tube heat exchanger, where it is heated using a shell inlet stream excuse me, having the same composition as the crude feed stream, and enters the shell of the heat exchanger at 180 degrees Celsius and 200 kilopascal, and this flow rate. So now the pressure drops on the tube and shell sides will be these respectively. You can write them down. You can pause the video and be coming back and forth, be shuffling between the HYSYS and the video. Now the two outlets from the heat exchanger is then sent to a desalter, which is simply modeled as a 3-phase separator where the desalted water, oil and gas is separated. Now the oil stream, light liquid from the desalter, is then heated to 175 degrees Celsius through a heater with a pressure drop of 375 kilopascal, and then sent to a pre-flash using a separator to reduce the light component in the feed. Now the liquid product from the separator is then heated to this temperature, and this is the pressure drop before entering the atmospheric column. Now the heat exchanger specification use a weighted model. The shell side outlet temperature is 95 degrees Celsius. Now calculate these. So we can go back to our HYSYS now. So the first thing was that we need, let's specify certain properties here. We're given the temperature to be at 15 degrees Celsius, the pressure was at 1000, then the flow was 6 exponential 5. So this has been fully specified. Then we need a water stream. Let's call this water composition. Okay, we can see H2O, it's not here, so we have to go and add it in properties. Okay, we've done that, so let's come back to our simulation environment. Active. So we can click on composition now and say our water is 1.0, just 1. So let's specify the conditions. Temperature is 15 degrees Celsius also. The pressure is 1000 kilopascal. The mass flow is 21,600. So yes, we've done that. So the next thing we need is a mixer, which is this here. We could do this. Let's call this mixer outlet. Okay, I think that's that. Okay, from the problem statement, the outlet of the mixer was heated to 65 degrees Celsius. So let's call this heater 1. The inlet will be, let's say, heated crude. Sorry, this should be let's delete this. Let's say this is heater Q, heater 1 Q. Okay, so that's the delta P was given to be 50. Then we are heating it to 65 degrees Celsius. So that's that for okay. So we can proceed to the next step. That's the heater outlet is fed into a tube and shell heat exchanger, but it's actually in the tube. So first and foremost, and also it states here that okay, let's go back to the slide so that I can read a part. Now, where it is heated using a shell inlet stream having the same composition as a crude feed stream. So let's go back to HYSYS and first create a stream. Let's call it pump around. So it has the same composition as a crude feed stream. So we are going to define from stream. We are going to define from this crude oil. But then we are going to change the conditions to be according to the problem statement 180 degrees, 200 kilopascal, and the flow rate is 175 meter cube per hour. So yes, this has been fully specified. So we can come here. The tube inlet should be heated crude. Let's call this heat exchanger. Heated crude. The two outlets should be, let's say this is heated crude 2. The shell pump around should be this. Then let's call this pump around 1. Unknown delta P, so we can come here and say so from our problem statement we're given that the shell dp is 5 while the tube dp, that's change in pressure, is 35. So we can now come also from our problem statement, we're told that the outlet, okay, let's go and check it. Okay, we should use simple weighted model. Then the outlet temperature is 95 degrees Celsius for the shell. That's the pump around 1. So okay, design. Okay, so we can come to design and parameters. Then the heat exchanger model, simple weighted model was what we asked to use. So that is that we are done. So we can come to the performance here and check the minimum approach, which is 30 degrees Celsius. We are asked to find out from the problem statement. So here's the minimum average. So we can close this and we can just okay, sorry about that. Let me just arrange this. Okay, so I just paused the video to arrange the heat exchanger. So back to our problem statement. Now let me go to the problem statement. Okay, now where it is heated using a shell, this, okay, using this, we are done with this part. So now the pressure drop is this. Okay, so the tube outlet from the heat exchanger is then sent to a desalter, which is simply modeled as a three-phase separator where the desalted water, oil and gas is separated. So let's go to desalter, a three-phase separator. The inlet is going to be heated crude 2. Let's call this desalter. Of course, the heaviest liquid will be the water, so let's call this the salted water. The light liquid will be the crude itself, crude oil rather. Let's just call this oil. Then this would be gas. So we're done. Just for arrangement, we can bring this here. Okay, I think we are good to go here. So back to our problem statement. Now the oil stream, which is a light liquid from the desalter, is then heated to this through a heater, and the pressure drop is this. Okay, let's put the heater here. Let's call this heater 2. Let's just call this Q2. Then the inlet will be the oil, the outlet will be heated oil. The delta P was given to be 375. Then it was heated to 75 degrees Celsius. So that's everything. Just in case it did not calculate, just click on ignore, then untick it, so it does the calculation. So let's arrange this. Let's make our work look a bit neat. So we can rename this to be Q1 so that it won't take a lot of space like that. So that is good. heated oil. So what's the next thing to do now? Okay, we've done it to here, and then sent to a pre-flash, which is a separator, to reduce the light component in the feed. So let's go back. It's a separator. Pre-flash. What's going into the pre-flash is the heated oil. Let's call this vapor outlet. Then let's call this oil 2, which is, let's look at the worksheet. Okay, so that's that. We can, let's go back to the problem statement to check the next step, to reduce the light component in the feed. I think that's all. Now the liquid product from the separator is then heated to 400 degrees Celsius inside a heater before entering the atmospheric column. Okay, so let's heat it. We can put it here. So let's call this our heater 3. Energy Q3. Let the outlet be atmospheric distillation column 1 in the inlet, or let's just call it preheated crude, because that's the end of the preheat train. The change in pressure was given to be 250 kilopascal, and it was heated to 400 degrees Celsius. So it should be 250. So that is that. I think this is everything we need to simulate. Okay, let's go back to our slide. Okay, calculate the vapor fraction of the product stream before entering the atmospheric column. That's the final one we simulated. Minimum approach. This is the temperature difference between the minimum temperature difference between the hot and cold stream, which I already showed you from the heat exchanger. So what we've not done is this, and this is the vapor molar flow rate from the pre-flash. So let's go back to the vapor molar flow rate from the pre-flash. Should be 0. The vapor molar flow rate should be 0. Then the initial one, which was the vapor fraction of the stream before entering the atmospheric column, that's here. The vapor fraction should be 0.7891. So that's all for this lecture. So we can save this file as instead of just saving it to the oil characterization file, we can save that as preheat train. Yes, we are done. So this is the entire preheat train. So let's, okay, that's all for today. I really hope you learned. Please try and simulate these on your own without checking the video after the entire process, so that you'd learn and it will stick to your mind that way. Thank you very much. Once again, this is Rainbow John for geniusescreed, and please do well to give this video a thumbs up if you learned something, and also subscribe to my YouTube channel. Thank you very much.